Forget delivery counts and quarterly charts. That version of the story is comfortable because it fits into familiar boxes. It lets everything be measured in units shipped and margins earned. But that story no longer explains what is actually happening. The real transformation is quieter, deeper, and far more consequential. It is not about a single vehicle or a single feature. It is about an industrial system being redesigned from the ground up, piece by piece, inside factories and software stacks that most people never see. Once you understand that system, it becomes impossible to look at the company as just another automaker. Imagine stepping back and looking not at products, but at momentum. What is unfolding is a chain reaction of advances in batteries, manufacturing, artificial intelligence, and energy infrastructure. Each advance would be meaningful on its own. Together, they compound. Cost reductions unlock new markets. New markets generate data. Data improves intelligence. Intelligence enables autonomy. Autonomy reshapes economics. This is not a straight line. It is a flywheel that accelerates as it turns. Over the next 5 years, this flywheel has the potential to change how vehicles are built, how they are powered, how they are driven, and how they interact with the world around them. The foundation of this shift begins with something most people will never touch or even see: a cylindrical battery cell defined by its dimensions rather than its name. On paper, it looks like a simple scaling exercise, a cell that is 46 millimeters wide and 80 millimeters tall instead of the smaller formats that came before. But the size is not the point. The point is what that size enables. For decades, batteries have been the choke point of electric vehicles. They're expensive, slow to manufacture, energy intensive to produce, and painfully difficult to scale. Traditional battery manufacturing relies on a wet process that is both messy and inefficient. Active materials are mixed into a slurry, coated onto metal foil, and then run through massive ovens to evaporate solvents. Those ovens consume enormous amounts of energy and space. They slow production and drive up cost. The shift to a dry electrode process is an attempt to erase that entire step. Instead of painting a wet paste and drying it, active material is pressed directly onto the foil as a dry powder. No solvent, no evaporation, no giant oven stretching the length of a football field. In theory, this slashes energy use, reduces factory footprint, and dramatically increases output speed. In practice, it is one of the hardest manufacturing challenges in modern industry. Getting dry material to adhere uniformly at high speed without cracking or shedding particles pushes the limits of material science and mechanical engineering. Early progress was slow and frustrating. Components failed, coatings cracked, scaling proved far harder than laboratory demonstrations suggested. What changed was persistence and iteration. After years of setbacks, the process matured. By the middle of the decade, internal production reached a point where cells manufactured in-house were already cheaper per kilowatt hour than cells purchased from suppliers, even before the dry cathode process was fully optimized. That detail matters because it flips the economics of electric vehicles. When the most expensive component becomes cheaper to make internally than to buy externally, control shifts decisively. Cost curves bend downward. Long-promised mass-market vehicles stop being hypothetical and start becoming inevitable. This battery is not just an energy container, it is a structural element. Instead of assembling cells into a heavy pack that is then bolted into a chassis, the pack itself becomes part of the vehicle's structure. The floor of the car is the battery. This removes hundreds of parts, reduces weight, increases stiffness, and improves safety. It allows more range from the same amount of energy and creates a platform strong enough to support heavy-duty applications and extremely high-mileage use cases. Without this integration, certain vehicles simply do not make economic sense. With it, they become viable. The chemistry inside these cells continues to evolve. Graphite anodes are reliable but limited. Silicon promises far higher energy density, but introduces severe mechanical stress as it expands and contracts during charging cycles. The challenge is not discovering silicon's potential, but controlling it. Blending it, structuring it, and engineering it so that it can repeatedly swell without destroying itself requires years of experimentation. Each incremental improvement translates directly into more range, longer lifespan, or faster charging. Beyond that lies the longer-term pursuit of solid-state batteries, where liquid electrolytes are replaced with solid materials. In theory, this improves safety, density, and durability all at once.
While still difficult to manufacture at scale, steady progress suggests that today's lithium-ion cells are not the final form. Batteries alone do not transform an industry. Manufacturing does. For more than a century, cars have been built in long linear assembly lines. Frames move slowly from station to station, accumulating parts along the way. This approach made sense when vehicles were simple and labor was cheap. It makes far less sense when vehicles are complex, heavy, and packed with electronics. A different approach reorganizes the factory itself. Instead of a single long line, the vehicle is broken into large modules that are built in parallel. Front section, rear section, central floor. Each module is fully assembled with motors, suspension, electronics, and wiring while it is still open and accessible. Only at the end are these modules joined together. This parallel approach changes everything. Workers and robots have unrestricted access. Installation is faster and more ergonomic. Errors are easier to catch. Production speed increases while factory footprint shrinks. Claims of double-digit improvements in throughput and massive reductions in required space are not marketing slogans. They are a direct consequence of eliminating unnecessary complexity. This method only works because of another breakthrough: large-scale casting. Traditional vehicle underbodies consist of dozens or even hundreds of stamped metal parts welded together by armies of robots. Large casting machines replace that complexity with a single piece of aluminum for the front or rear of the vehicle. Hundreds of welds disappear. Hundreds of robots become unnecessary. Space is freed. Weight is reduced. Strength improves. Most importantly, production time collapses. The cast part becomes a foundational module that slots neatly into the parallel assembly process. The real advantage is not the machine itself, but the expertise behind it. Developing alloys that can be cast quickly, cool properly, and remain strong without becoming brittle is not trivial. It takes years of iteration and produces a knowledge base that is difficult to replicate. As manufacturing becomes simpler and faster, the internal systems of the vehicle must evolve as well. For decades, the automotive world has relied on a 12-volt electrical architecture. That standard dates back to an era of headlights and radios. Modern vehicles are rolling computers with motors, pumps, sensors, screens, and processors. The physics are unforgiving. Power equals voltage multiplied by current. If voltage stays low and power demand rises, current must increase. High current means thick copper wires, heavy harnesses, and significant energy lost as heat. Wiring looms in modern vehicles can weigh more than a small passenger. Moving to a 48-volt system changes the equation. Quadrupling voltage allows current to drop by a factor of 4 for the same power. Heat losses fall dramatically. Wires become thinner, lighter, and cheaper. Entire wiring architectures can be simplified. Power and data can share common pathways, replacing the tangled one function per wire approach of the past. This shift is not merely an internal optimization, it disrupts the entire supplier ecosystem built around 12-volt components. Motors, pumps, and controllers must be redesigned. Companies deeply invested in legacy standards cannot pivot quickly. Vertical integration becomes an advantage because it allows rapid adoption without waiting for the supply chain to catch up. All of this manufacturing and hardware progress sets the stage for intelligence. For years, driver assistance systems relied on rule-based software. Engineers attempted to encode the world in conditional statements. If this happens, do that. This approach breaks down in the real world, where edge cases are infinite and context matters. A stop sign partially obscured by foliage, a construction worker directing traffic against a signal, a confusing intersection in bad weather. No rulebook can cover everything. The shift to an end-to-end neural network represents a fundamental change. Instead of telling the system how to drive, engineers show it how humans drive. Millions of video clips become training data. The system learns patterns, not rules. It predicts the most likely next action based on everything it has seen before. This is not magic, it is statistics at massive scale. The more data it sees, the better it becomes. Importantly, this improvement is continuous. When a human intervenes, that moment becomes a lesson. Over time, rare scenarios become less rare in the training set. Data alone is not enough. Training such systems requires immense computing power. Early approaches separated training hardware from the chips used in vehicles. That separation introduced inefficiencies. A unified architecture where the same class of chip powers both training clusters and in-vehicle inference tightens the feedback.
Improvements in hardware benefit both domains simultaneously. Training becomes faster, deployment becomes more efficient. This creates a reinforcing cycle that is difficult for competitors with fragmented architectures to match. If and when full autonomy is achieved without human supervision, the economic implications are profound. A vehicle that can operate continuously transforms from a depreciating asset into a productive one. Transportation shifts from ownership to access. Dense urban areas change as parking becomes less necessary. The cost per mile of mobility falls dramatically. Entire business models are disrupted. This outcome is not guaranteed. Regulatory approval, safety validation, and public trust remain significant hurdles. But the direction of progress is no longer theoretical. Each software update demonstrates tangible improvement. Beyond mobility lies energy. Electric vehicles are large mobile batteries. For most of their lives, they sit idle. Bidirectional charging turns that idle capacity into an asset. A vehicle can draw power when electricity is cheap and abundant and feed it back when demand is high. It can power a home during an outage. Scaled across millions of vehicles, this creates a distributed energy storage network that stabilizes grids and complements renewable generation. Implementation is complex. Utilities are conservative. Standards vary. Hardware compatibility matters. But the incentive is clear. Energy becomes something the vehicle participates in, not just consumes. Over the next 5 years, these elements continue to converge. Cheaper batteries reduce vehicle cost. Structural integration simplifies production. New electrical architectures cut weight and complexity. Artificial intelligence improves driving capability. Autonomous fleets generate revenue and data. Vehicles interact with the energy grid, smoothing demand and supply. Each component reinforces the others. None of this depends on a single announcement or product launch. It depends on execution across factories, labs, and code bases. The path is not smooth. Manufacturing breakthroughs are painful to scale. Regulations move slowly. Technical challenges remain. But the blueprint is visible. What is emerging is not just a new kind of car, but a new kind of industrial platform. Transportation, energy, and intelligence intertwine. Cities adapt, economics shift. The change does not ask for permission. It happens incrementally, then